So my brother designs escape rooms for a living. I don't know if you've ever played those, but they're a lot of fun. I promise this video is not about escape rooms, but more the technology behind them. So being a tech expert, my brother often comes to me asking for new fun tech puzzles to integrate in their games. So take a look at this guy here. So I've got two puzzles. They talk to each other, and you have to exchange sort of data across them. See if I can get this right. Oh, I got it wrong. But these two things will be spread out across different ends of the room, and when you get it right, maybe a door opens or something. So these guys have to exchange data with each other about the state of their puzzle, different key cards that are placed on the different puzzles, and they do that using a little bus like this. And if you've done electronics for a while, you might think this is a CAN bus, and it's a pretty simple two-wire bus, and you're close, but not quite there. So Controller Area Network, developed by Bosch in the late 80s. It's a linked local network where different electronic control units can talk to each other over a two-wire twisted pair. Now, pretty much every car made in the last 20 years, and German cars maybe the last 30 years, rely on CAN bus to send messages and data across the car. However, in recent years, there's been a bit of a trend to go Ethernet for all the things. You see, all around the world, we have all sorts of different communication buses that are specifically used in different industries. So CAN is widespread in automotive. FlexRay was at one point used in automotive. Aviation has protocols such as Airing 429, which is a disaster from the 70s. All kinds of other specific use case protocols like this. And when we have these specific protocols, every time we hit a boundary between two networks, we have to totally translate all of that data. So for example, I've got my escape game puzzles here. Maybe I want to run a web UI so that the puzzle master can look and see what they're entering wrong in the puzzle. Or maybe I have some sort of puzzle server that does this for all of the different puzzles, and I want all of my puzzles to communicate back with the server so that the puzzle master can see what's going on, stuff like that. So if I hit a boundary like that, now the computer speaks Ethernet, these guys speak CAN, now I need CAN gateways, things like that. And that just gets expensive and complicated really fast. So if we could make these guys just speak Ethernet, then we could speak like IPv6, IPv4, bridge them out to the internet if we want to, the cloud, all that kind of stuff. Because once we speak Ethernet IP, the ability to translate these protocols and route them across the world goes up very easily. So today I'm taking a look at a new standard, Automotive Ethernet 10Base-T1S, multi-drop Ethernet. This essentially has the same topology as the old CAN buses, running over a twisted pair, but gives us 10 megabit Ethernet and all of the advantages that Ethernet comes with. These guys can do MDNS. I can talk to them from my computer. I can flash them with just regular TCP. They speak multicast to each other. All this fun stuff we get with IP just magically over a two-wire bus. So if you're interested in the Mantis boards I'm using, they're available online now, and the T1S protocol in general, then come along on this adventure. So just for your guys' fun, here's how the game is actually played. So first you have to find these two things and put them each on one of the control pads. This is just sort of a prototype. But then you have to push the buttons in the right order. So if I push this button here, that lit up and was correct because I didn't get a red. But if I push the wrong button, it'll tell me what order it was supposed to be and then tell me I was wrong. So in this case, this one has to go first, this one has to go second, third, fourth, fifth, sixth, seventh, and eighth. So there we go, we won. So next I'm going to go over here and bring in the Mantis bridge. So this is the bridge that they sell alongside these boards here from Silicognition. The Mantis bridge, MAN-T1S. So this takes a normal 10 megabit Ethernet and it converts it to the shared bus here, T1S. And it also takes PoE power and powers the bus with 48 volts. So this guy is two twisted pairs here carrying 48 volt power and also 10 megabit Ethernet up to about 30 meters. And so I can just daisy chain them down this. I can have up to 8 devices on one segment, which is pretty cool. And then I can bridge this to a standard Ethernet switch to do things like multicast filtering between my different segments. I can unicast to these guys, etc. So before I jump into the weeds on how I'm implementing all this in software, how I'm making it look kind of like a CAN bus over multicast, etc., let's take a little bit of a look at the hardware. So these guys are called the Mantis. They were sent to me by their manufacturer, which is called Silicognition out of Colorado. As far as I can tell, this is one guy who makes these dev boards for Ethernet 10Base-T1S. He also makes another one for just plain wired Ethernet called the WESP, if you've heard of that one before. They're ESP32 based. So he sent me these guys to take a look at. Very thankful to him for that. He's starting a crowdfunding for these, so if you want to get one, currently as of the making of this video, you can get one there. Of course, this is a full standard, so there is plenty of other manufacturers that make equipment like this. Some of it's not very reasonably priced because it's designed for like automotive test engineers and stuff like that, but I've even found as much as like a USB 10Base-T1S NIC on Amazon, but it's actually more than this is. So here's all the stuff he sent me, the Mantis itself, and some accessories. So taking a look at the Mantis itself first, it's a castellated board, so you can solder it directly onto a board below it, or solder through headers. Flipping it over, it says Mantis, obviously. He's helpfully silkscreened what all the IOs are, so these are all the ESP32 IO numbers, different voltages available, etc. I used literally every single one of these pins, except the ones in the programming header for my example. So looking at the front of the board, this guy is the main IC. It's an ESP32 Pico V3. This guy here is the transceiver chip. I guess I'll put the model number on screen. It's just as the T1S Phi. It's just connected to the standard ESP32 MAC. You can also connect an antenna if you need over this little connector here. He's got a, it's called a quick header here if you want some I2C stuff. And all the other pins are brought out to the castellated pins or the programming header. It's got a power supply to take 48 volts from the bus to power itself. The bus itself is this little screw terminal connector here. So there isn't exactly a standard connector outside of like automotive connectors. So he just got this, and there's just two copies of the same bus. So it's a 2-wire bus. You can daisy chain it through by using the extra screw terminals. So next up, I got the Mantis bridge. This guy bridges from 10100 RJ45 Ethernet to T1S 10 meg multi-drop. Not that many pins for you to access here, but he's brought out the PoE voltages, the regulator voltages, as well as the I2C bus and the bus for configuring the Phi. He's also got bus termination resistors here with jumpers up here. Now I just left these terminators in place, so this guy was terminating my bus in the middle of the bus. That seemed to be fine. As for the architecture of this board, he's got the T1S Phi, and then this guy here is a small switch chip. So it has integral 10-100 Ethernet on this side, and there's a small microcontroller that just boots up and configures these chips so they pass traffic. But this is just a 2-port switch, so it's not doing anything to the Ethernet frames other than storing and forwarding them for one cycle, essentially. This also does PoE pass-through, so it takes in 48-volt PoE power here and sends that on to the 2-wire shared Ethernet bus, so you can power all the downstream devices, and that's how I've been powering everything today. So next little board he sent me, this is just a bus power supply. So you've got the daisy chain through on the bus. This doesn't actually have a Phi, it's strictly taking voltage from the DC input here and powering the bus with it. So that's all that's going on with this guy. And last thing he sent, this is just a programmer. So it's got USB Type-C and it's got a built-in Silicon Labs UART chip. So you can stick this through the holes here and just kind of hold it with your finger and use that to program the ESP32 over serial. This is actually made for his WESP product, which is why it's black instead of green. So one of the big drivers for this whole single pair Ethernet in the automotive industry is going from like a function-based network to a zone-based network. So I worked in automotive before. We had 2 CAN buses on the cars back at the time. This was 10 years ago. The body CAN, the chassis CAN. So on the body CAN, we have modules like self-leveling headlights, powered sliding doors, powered lift gates, the radio. Those are all speaking to the body because they're things the occupants and interiors deal with. But then on chassis CAN, we have stuff like the engine, transmission, transfer case, active suspension, adaptive cruise control, all of that. And notice that on both of these buses, we have components all around the car. So both of these buses have to run front to back, side to side, whole length of the car. And so that's essentially twice as much twisted pair because we have body CAN and chassis CAN running across the car. As we start moving to higher speed buses, it gets even worse. We have gateways all over the place. So by moving to like a zonal architecture, car company can say, here is the bus for the front of the car. Everything under the hood is all connected to the front of car bus. Doesn't matter what system it is, because if it speaks Ethernet, T1S, or higher speed Ethernet, if it's like a camera or radar or something, we can take that back to our Ethernet switch and send it where it needs to go. We don't have to have separate buses for separate functional systems. And so T1S fully supports that. So T1S can have up to 8 devices officially per mixing segment, they call it. Officially, it supports up to 25 meters. I tested about 20 meters in my house here, and it worked fine. I'm just using Cat5e. I just pulled the 4 pairs out, and I'm just using one of the pairs. This is the green one. I've got the blue one. I think I threw away the other 2, but I'm just using standard Cat5e here. I actually crimped on some RJ45 just using the center pair and ran this across my home, and I put these in separate rooms. I put the Mantis bridge in the middle down on my rack here with my PoE switch. Worked great. So that's with the terminating resistors in the center of the bus, which is probably not correct, but it's probably half decent. And about 10 meters in each direction, and it worked fine for me. So now that I got Wireshark open up, I'm going to go ahead and plug in the board. And once these guys boot up, we should start seeing some packets. There they go. So you can see we got a bunch of multicast traffic here, standard stuff, router solicitation, multicast listener report, and then we end up with a bunch of stuff on port 666 here. So what if I open this guy up and let's follow that UDP stream. So this looks a lot like the console output from one of these systems. So it says system has rebooted because of power up. This guy's name is Mantis 91D1F. We did a bunch of configuration and we're ready to go. So that guy was 1D1F. So if I come back to the full capture, I've also got D53B. So let's follow his conversation. And his looks similar. So he's 90D53B. And he also booted up initialized. So this is mostly debugging aid for myself. So I could plug in the USB serial port to debug it, but I got a network, so why not? So basically I rerouted the output console from the Mantis, the ESP32, to just send a UDP packet to multicast every time. So as long as my laptop subscribes to that multicast group, I just get a UDP stream full of all of the debug messages. Super handy. I can filter them by who they came from. Each of these guys has a unique link local IP address, so I can just see what IP address did it come from. And I got debugging. And I can also flash them over Ethernet as well. So for example, I just want to flash 9ED53B.local. That's just a MDNS name, so I can just send it puzzle bin, and there we go. It should say OTA starting. I should see what's going on. It's not the fastest thing in the world. And there it goes. And over here, if I follow this TCP stream, you can see it's from 2 link locals to each other. So one of these is the target and the other one is my laptop, and if I follow that, I should see, yeah, there's all the firmware update being sent. So back in the days of a CAN bus, essentially all of our transmissions were broadcast. We had IDs, they were either 11-bit or 29-bit, which is kind of a weird number, but whatever. And we would just know that each ID means certain bits of data. We couldn't format the data with something nice like JSON or XML. God, XML weighs so much data. But with only 64 bits per message, we had to bit pack everything we needed. And then on the bus, we would say, like, I want message number 72, etc. And we didn't have essentially more meaning to that. And if I wanted to, like, flash one of these modules, I would have to allocate one of these multicast addresses for flashing that module, or we'd have to go through some rigmarole of, like, taking control of that temporarily for the flashing purpose. But with this, I'm on Ethernet. So all the rules of Ethernet apply. I have broadcast, which we don't use that often, but I have multicast, so I can use multicast groups to sort of simulate what we had on the CAN bus. So if I want to send data between these 2 nodes, they can send it to a multicast group ID. But I also have unicast. So if my laptop wants to do reflashing or something, it can get the unicast IP address of one of these boards and talk to it specifically. Now, over T1S, we essentially don't have like a multicast aware switch, but this is connected up to my switch in the closet, which is multicast aware. So we can have the switch at the end of the segment filter out multicasts that don't need to go down to this segment, so we're not wasting our 10 megabits of bandwidth with data that's shared with only other systems that aren't on this bus. But all of that is IP standard stuff. None of this is specific to T1 Ethernet, CAN, any of that stuff. This is IGMP and IPv4, or multicast listener discover in IPv6. And it works entirely correctly over this bus. So these guys can pretend like they have a CAN bus, but really they're bridged to the outside world. And as for pretending they have a CAN bus, this is the data I'm actually sending. So I've got 4, 5, 6, 7, 8, 9 bytes of data here. And if this was a CAN bus, I would have had to struggle to bit pack all of these to make perfect use of my data. But this is IP, so I can just use uint dates for IDs and stuff. And let's see what this looks like in Wireshark. So down here I've got a whole bunch of these going. So they're both sending multicasts from their own address to 6969. And just pop open that frame. You can see it's 12 bytes long because it padded it. But I've got, in this case, I got all zeros. Let's pick a more interesting one. Maybe I should like wake the puzzle up and have the puzzle start doing stuff. Let's see. Okay, one of these is probably interesting. So I've got 1, 2, 3, 4 bytes of sequence number that are all zeros. I got a 0, 2. What is that? Okay, 0, 2 active. Okay, so then I expect a button, which probably won't be anything. The phase, the leader, the output. Okay, so I'm looking for something in the active, the phase, and the output. And that's exactly what I got. So we're active 02, phase 03, and the output would be 01. The output's a bit mask, so LED 1 is the first bit, and that looks correct. Also, if you're like doing this like for real products, you can write your own WireGuard dissectors in Lua and load them in. So WireGuard can dissect all of your custom protocols you're using across your pseudo CAN bus at higher speed, which I didn't take the time to do for this video, but is absolutely something that you should do if you make a product based on T1S. Last neat thing I did here is a multicast printer. So basically what this does is this in Python listens for that multicast group, 6969, and it decodes some of the bytes just by looking at the byte array raw to decide if it should print the thing off the printer. So the way this game works, when you win the game, so if I can, I lost it. When you win the game, it prints off a clue to the next puzzle on the printer. So since these guys are hooked up to Ethernet, I can just have some Python code that I wrote real quick that listens to the multicast these guys are sending, and when we get to the right state, the winning state, it just sends a job to the printer. I just wrote this for my Mac because it was nice and simple, but this could run on some server somewhere, could run, we have cups. I mean, the printer's not the point. The point is that these guys talk Ethernet, and that makes it really easy to interact with the outside world. So having nice hardware is great and all, but that's really nothing without good software support. Now thankfully, this board is based on the ESP32, which has a thriving software ecosystem. So Silica Ignition is shipping these Mantis boards with MicroPython pre-installed, so you can use a serial console or WebSocket to write Python code live. If you're looking for a really easy way to develop, MicroPython's probably it. For a bit of a step up, you also have ESP Home. If you're building like home automation gadgets linked together with T1S, that's probably a great application for single pair Ethernet as well, at the sort of room scale where the 25-meter length limit would kind of apply. So you could have a bunch of sensors, actuators, and stuff, all daisy-chained together in the same room, and you can control that all with ESP Home. So the Mantis has upstream support in ESP Home now as well. I chose the hard mode approach. I am an embedded programmer, or I guess I was before I became a YouTuber, and so I am perfectly happy writing bare C code, compiling it. So I used Espressif's ESP32 IDF. This is the very excellent dev chain from the chip manufacturer Espressif. They actually have a Visual Studio Code plugin, so I didn't have to install any software manually. I can just load the plugin in VS Code, and then it goes and downloads all the tool chains, all the libraries I need, and it's ready to go. So that's what I did for this project. So the reason I chose to go straight to the C coding instead of using an easier approach like ESP Home or MicroPython is mostly because of the IPv6 support in ESP-IDF. So with modern ESP32 framework versions, IPv6 is a total first-class citizen, enabled by default, super easy to use. Now, I can't say the same for ESP Home, where it's enabled by default, but it still requires v4 to function, or MicroPython, which doesn't yet have IPv6 support on the ESP32 port. So for me, using IPv6, it was no-brainer to use ESP-IDF. Also, Espressif's documentation is actually incredibly good, and I found many great examples from their own documentation site. So I've posted all of my own code on GitHub. You're free to read it. Now, Espressif has a lot of design considerations that are mostly designed around people using their chips for products. So like reaching out to the internet to download a cloud image. So I wrote my own OTA loader that just uses basic TCP with Netcat. No sort of security there, but I'm on my own local network. I wrote a little bit of code to do multicast, to simulate the CAN bus IDs, that kind of thing, to share data between the puzzles. And I wrote a little bit of code to do that network debugging, but all of that's on my GitHub as well. You're free to read it. But the real star of IPv6 here is automatic link local addressing. So I got this game puzzle. I got two stations, and they're located in different parts of the room, but they both run the same firmware image, and the way they talk to each other, they actually negotiate who's going to be the leader. So one becomes active 1, one becomes active 2, and whoever becomes active 2 first becomes the leader. So they don't actually need to know each other's ID, and I don't have to pre-assign one of them as the sort of leader. The problem with that is, how do I decide what their IP addresses are? So imagine I have a subnet like 192.168.1.0/24, and I'm going to make one of the puzzles .1 and one of them .2. And they need to retain this IP address forever so they can keep talking to each other. But how do they decide what their IP address is? I could just hardcode the IP address into the firmware file. Then I got to recompile it for my two different boards. I could use DHCP, but then I got to stand up a DHCP server just for these two things that talk to each other. And so what I use instead is IPv6 link local addresses. So you start with FE80, and then they have a 64-bit unique identifier that comes from the MAC address. So each of these boards has a unique MAC address. Each of them has a unique link local address. It just works. Now, because IPv6 normally has more than one address per interface, and actually the ESP32 supports up to 5 per interface, so we have our one link local and up to 4 more, I can give them global addresses that are routable around the world if they need to reach out to the cloud, but they can still use their local addresses to talk to each other to negotiate the puzzle. And the presence of a global address doesn't deter them from still talking to each other with their link local address. So in IPv4, if you were to do the 169.254 trick, which is valid IPv4 link local addressing, then you can only talk to each other, and if you suddenly get global connectivity from DHCP, then you have to figure out each other's new IP address because you don't have more than one IP address at a time. So that's why I've chosen to use IPv6 for this, to make use of the link local addresses for machine-to-machine communication on the same bus, with the possibility of using global addresses for remote flashing or other optional features that don't directly impact the functionality of this. So then, since I'm using IPv6 link locals, I also need IPv6 multicast addresses. I chose to use the link local scope, which is FF02, and I just put a random number on the end, 6969. So that's basically it for that. Now the ESP IDF fully supports multicast listener discovery. So if you hook this up to a network that's doing MLD probing, it'll find the multicast groups that this particular ESP wants to speak. But in my case, I have that all turned off because this is just on a purely link local network with just my laptop and the two mantises. So I hope you guys have enjoyed my dive here into 10Base-T1S 10 megabit multi-drop twisted pair Ethernet. This is one of the T1 Automotive Ethernet families. So my first use for T1, maybe about 10 years ago, I was working with a auto drive team at my university. They were trying to set up a forward-facing radar from a car and integrate it into their autonomous system, and it spoke 100Base-T1. So that was the first of the sort of T1 standards. So if you've heard of like 100Base-T, 1G-Base-T, those are the twisted pair standards. But the T1 versions all use one single pair. So, I don't know, was it 15 years ago or so, Broader Reach tried to develop a 33-meter, 100 meg single pair so that automotive cameras could use one pair instead of two to save on copper. Eventually they were able to get gigabit to run over a single pair as well, so that's why we have 1000Base-T1 single pair Ethernet. And then finally they went back to 10 meg because it turned out at 10 meg there were some really big advantages as well. So here with T1S, we're able to do multi-drop at 10 megabits. Over the same distance, we could do 100 meg point-to-point. And so that gives us essentially the functionality of a CAN bus, but at 10 times the speed and with standard Ethernet. The other option for 10 meg is to do ultra-long distance. So T1S is the sort of short-range version, multi-drop. There's also T1L, long-range 10 megabit Ethernet, and that can go several kilometers over a phone twisted pair. So if you have to send security cameras or something ultra long distances, that might be easier than using something like DSL. I've also really enjoyed taking a look at these other unique Ethernet transports. So obviously today I took a look at T1S, which replaces CAN bus. In the past I've looked at GPON, passive optical networking fiber, Wi-Fi Halo, 900 megahertz, sort of odd Wi-Fi standard. But I love all of those kinds of things. And all the ways we're taking all of these weird, industry specific, even if they were standard protocols, and converting them all to something that's pretty universal, Ethernet and the Internet Protocol. So looking forward, I'm really trying to get my hands on some Li-Fi. That's the infrared light-based technology. So there's an IEEE standard for it and an ITU standard, and they're both different, of course. I'm trying to get my hands on either one of them, but so far I haven't been able to get in contact with anyone. So if you can help me get some Wi-Fi equipment, I would be mega down for that. I'm also taking a look at some more fiber-based networking. So I'm trying to do a CWM and a DWM, like regional and wide-scale network lab in my office in Finland. These guys, of course, the short-range T1S, have been really cool for me for the applications in home automation, like room scale, networking of things. I mean, of course, you could use Wi-Fi, but Wi-Fi is always congested. And for stuff like this, I would have to prepare each one with unique keys and stuff, or generate them based on the MAC address, and that's a lot harder than just plugging them in with a wire, especially because they need power anyway, and the Ethernet bus provides that power, which is super cool. Also, big thanks to Silica Ignition for sending over these Mantis boards. They're available on Crowd Supply now. He's in the crowdfunding phase, but he's already reached his funding limit, so he's going to go through. Now, of course, disclaimers, crowdfunding is never a guarantee. However, it's not his first time, it's not his first rodeo. The Mantis is not his first board, and it's also not a very expensive board, to be honest. So I have quite a bit of confidence this will go through. Let's go ahead and check him out there. This is definitely the cheapest way to get into 10Base-T1S. If you have an application where you're looking to replace some old school legacy bus with modern Ethernet. If you want to chat with me, link down below for my Discord server. If you want to buy my shirts, I make shirts now, such as this beautiful Home Lab, your own personal data center. I also sell this one in gray now, so pictures on my site for that. Link down below to my Ko-fi to buy one of these there. If you want to chat with me on Mastodon, I'm on Mastodon. It's kind of like the Dead Bird site, but it's not a bird. And I guess I'll see you guys on the next adventure.